in this video, we're going to talk about continuity and one-side limits. So we see two pictures here, F and G. These are exactly the same. They have the same limits everywhere. However, G is not continuous and F is. So keep these pictures in mind. Interval notation, just as a recap, an interval uses X values. If we see parentheses, that means the endpoints are not included. These will always be X values, like a first X value and a second X value. This is not an ordered pair if it's an interval. If we see a closed interval, we're going to use brackets. Again, one could be included, one could not be included. So continuity just means there's no interruption at a point. So when we talk about continuity, we talk about at every single point. So basically, can you trace it without lifting your pencil? A function can be continuous everywhere or in an interval. Here, F is continuous everywhere because I can trace it without ever lifting my pencil. G of X is continuous everywhere except right here when X equals 2. So if we're talking about a point here at 2, we say it's not continuous. If I asked you, is G continuous? We would say, yes, it is. It is at every single point except right at 2. So we never really say it's not continuous. It's not continuous at one specific point. So here's your definition. This little plus means a limit from the right, and the little minus means the limit from the left. Remember, we're looking as we get really close to some value. If it is continuous, then the value at X equals C will also be equal. So all three of these have to be equal. If we have a piecewise function, that will create a jump. That means these two will not be equal. If we have a hole, as we did in our previous picture, then it will not equal the function value. Again, if you can trace it everywhere, then it's always continuous. Whenever you have to pick it up, that's a place where it's not continuous. We call that discontinuous. So here are some examples of discontinuity. So our first one, our limit, meaning where we approach from the left and from the right, this guy does exist, but this guy doesn't exist because it's an open circle. So they're not equal. If we look at the next example, the limit as we approach from the left does not equal the limit as we approach the right. From the left, we have a limit of 4, and from the right, we have a limit of 5. Those are not equal, so we don't even have to check the third condition. We know this is not continuous. If we look at the last example here, we have a vertical asymptote. The limit doesn't exist because it approaches infinity, and f of 0 doesn't exist because it's never, ever, ever going to hit x equals 0. So types of discontinuity. Removable is going to create a hole. If we can factor and cancel and remove the hole, then it's removable. And that just means it's going to look something like this guy or this guy. The one in the middle is a non-removable or a jump discontinuity, and that just means we kind of have to jump from one value to continue the function. Factoring isn't going to help us here. Also, piecewise creates a possible jump discontinuity. So our example, it's just going to say discuss. So we got to check every single point, and obviously we can't. We know in a rational expression, we really do not like when the bottom is 0. So here, at x equals positive 2, we have some type of discontinuity. That means not continuous, discontinuity. So this means it's not continuous right at 2. We have to pick up our pencil. Now we want to know what kind of discontinuity. So if we can factor the numerator, and we can into x minus 2, x minus 3, if this eliminates that hole, then it's removable. So in this case, we can cancel, and we're left with this graph. So this graph and this graph are exactly the same except at 2, and that means there's a hole at 2. So this is going to look similar to our very first picture that I put up on the board. So you can see I have drawn pictures, and these two graphs are exactly the same. It's just that our original has a hole at 2 and our new one does not. So if we were to find the limit, we could use either one. In this case, it wants to know when it's continuous. When do you have to pick up your pencil? And you have to pick up your pencil at 2. And because in our answer there is no discontinuity, that means that they hold. That means it is removable. So the way we would answer this is we would say there is a removable discontinuity when x equals 2. And that just means it is a hole, but it's just a hole. It's not a jump. So here are some theorems. We're not too picky on the theorems. You know, in order for the limit to exist, they have to be the same from the left and the right. We've talked about that before. Properties of continuity, if we have 2 continuous functions, and that should say f plus or minus, their composition is also continuous. And then finally, the intermediate value theorem. I'm going to explain that in a little bit more detail here in another slide. So again, limits from the left and right must be equal. So here this is a piecewise function, but the limits from the left and the right are both approaching 4. So the limit exists. If we look on the right here, we approach 2 completely different y values. So here the limit does not exist. And then intermediate value theorem, you can look at all this, but basically in order, if we have a continuous function, that means we have to be able to trace it and never lift our pencil. If we know that we have one endpoint at 0 and another endpoint at 3, that means somewhere in here we have to hit every y value. We have to be able to find a point on our line that corresponds with every y value in between. Otherwise, we would have had to pick up our pencil. So one example, it says, does the intermediate value theorem guarantee that this has a 0? So first of all, this is continuous. So the intermediate value theorem must apply. We need to find both of our endpoints, so we're going to plug them in. So when we find our corresponding ordered pairs, we see that at 0 we have a y value of -1, and at 1 we have a y value of -2. Because we're going from a negative value to a positive value, yes, we have to hit 0. The intermediate value theorem guarantees it because it's continuous. So a visualization of this, if I know that my function is starting at 0, -1, and I know it's finishing at 1, 2, there's no way for me to get from this first point to this second without crossing 0. So it has to cross there sometimes. If it doesn't, then it's not continuous. And because this is a polynomial, we know that it's continuous. So here we'll say yes, intermediate value theorem guarantees a 0. And you don't have to explain any further because you use the theorem and you've shown the work to support your theorem. You would need to write in words, though, that this function is continuous because it's a polynomial.